Ah. All right. Let's see. The pole with it. All right, here you got a poll going. Scales. Warm up with some scales. And go live. We are live. And we've got ourselves a friendly little reminder, everyone, that, oh, hello, Abdul Rahman, aka old friend. All right, so we're going live. We have, we're marching towards complete proficiency as far as integration is concerned. Please remember the map of the basic integration map. So here's the chart of all integral problems, and then we're gonna become like world experts at that many integrals. I don't know if you can see that. See that? Yeah. We're gonna become good at that territory. Okay. And so the question that motivates this week and the homework of this week, the one that's due at the end of the week. That's right, B-boy. That's absolutely, you have the right intuition. That's right. So we had to ask, in that speck of mold, as B-boy likes to call it, what kinds of integrals can we be like, can we feel good about, in the sense that like when we see it in nature, we'll know that we have the tools to crack it. Okay, what kinds of integrals? And that's motivating question for the first like chunk of the class. The very like puzzle solving type of mode that we're in. Okay, and this week The question will be, can we integrate expressions, certain expressions that involve trig functions, like sine and cosine? This week, it's forward trig functions. Then, like next week, we'll see the usefulness of sometimes thinking about inverse trig function, like arcsine, arccosine, arctangent, etc. So today we do like forward functions, and we see. So there's a poll happening right now. Everyone excited about integrating trig functions. I expect 100% of the responses to be yes, of course. All 15 of you. 15 out of the 33 students in the class. Go. Okay, so I do know that students are in the process of reviewing what they learned at the end of Calc 1. They still have some lingering questions about substitution, and mostly it's questions about substitution. Integration by parts seems to be, in a sense, easier to execute. But substitution seems to be still a lingering issue. Okay, so what I'm going to do here is appeal to my students. Okay, not sure. But I'm going to appeal to my students. Go flood the voice channel on Discord. And because we have an incoming little problem just to get, before we begin the discussion on trig functions and how to integrate them, I just want to wrap some stuff up. So go flood general, the generals of Discord, assemble. We have an incoming problem, right? You guys want to see an incoming problem screen? Let's see. Which one should I do? Okay.
Incoming problem.
Okay, we got a
Incoming problem.
situation.
Incoming problem.
Apologies, it sounds really
Incoming
loud.
problem.
All right, in the meantime, let me get
Incoming
my
problem.
up.
Incoming problem. Incoming problem. Incoming problem.
All right, and we're back. We're back. And the issue is this. Here you have this integral right here. How should we approach this integral? That's the basic question. What techniques will crack this integration problem? So now I'm going to go into the general Discord channel and hear my awesome students, all of them participating. Amazing. I'm going to go listen to what they have to say. Okay, students, I'm here now. Somebody, brave soul, tell me, how the hell do you approach this integral right here? Anyone speak?
Would you separate it into three integrals? And then
Awesome. RAC, rack. Rack is right. Thank you, rack. So first, notice that it's three integrals. Awesome contribution. Thank you for that. Okay, more. Okay, but does that doesn't solve it? That in fact, you took one problem and made it into three. So in a sense, you made it worse. But okay, next.
The first integral is you can just do directly. This.
Yeah. So this one you just say, okay, easy peasy. Okay, forget it. X squared over 2. Divine inspiration, or whatever. What did we call it? Direct inspection. Okay, whatever. Divine inspiration. Okay, that technique where you just know it when you see it. Okay, good. So good. That's the dumb one. What about the second one? Stage 2, or second part. And by the way, that person who just spoke up, their name is hard to pronounce, because let me tell you what their name is. For those of you who can't see, their name is literally this. So I don't know how to say your name. Do I just pause for a moment?
No, I just changed it to the same thing that's in the Twitch stream.
Okay, so it's
harder to pronounce now.
Okay, that's not a, that's Shrek. So Shrek. Shrek, tell me how to do the second integral then.
It should be integration by parts.
That's absolutely correct. This parts will crack this, and I'll tell you what parts will crack it. You want u to be the ln x1 and dv to be x dx. And because when you do du, when you differentiate u, you'll get 1 over x dx. And when you do v, you'll get x squared over 2. And when you assemble v times du, it'll be a much friendlier integral. So this is, the trade-off is profitable. Parts will help you out in this integral. So that's right. That's how you would do it. I'm not going to do the integral. I wanted to say how to approach it. Okay. Next, this one, crazy. So Shrek or whoever, Rack, Shrek, whatever.
Substitution.
Substitution. Shrek says substitute. Okay, exactly. And this is where I had some questions, where students had some questions. This thing crumbles with substitution. And what will you substitute?
The bottom, 1 plus x squared.
Yeah, the whole bottom, right? The whole thing. Because that'll be, because the one, okay, so let's do that. The whole thing gets quarantined as, I guess, u. Usually, people just have decided that you can use u as the new variable. You don't have to. And it gets extra confusing when you put u here and you had a u earlier in the computation. As long as it's straight in your mind that I've reset the name of u, it's all good. So u equals x squared plus 1. And then, so that's the name of the substitution. And then what you do next is, the next thing you write is how the substitution is going to replace the dx part of the expression. And to get there, you differentiate the substitution rule. So the way we write this is you just write formally the symbol du as the derivative of this quarantined expression with respect to x. And you get 2x dx. Okay, so you put both of these down on the page when trying to execute a substitution problem. And what you then do is see whether the integral nicely transforms completely, including the dx symbol, into something that's just involving u's, and hopefully it's a profitable trade-off. It's a nice expression in the u's. So let me actually try to execute this way down on the bottom here. So x over 1 over x squared. This is because a wonderful student asked a question how to do substitution, essentially. So here we go. I'm going to execute it here. And if you see how this one works, you'll see how like all of them work in Spirit. So du is 2x dx. Okay. So what I do here is I try to like transform this entire expression into u's. And I do it like with trying to cordon off entire chunks. Bigger chunks I can cordon off easily, the better. So like, for example, here's a chunk, x times dx is right here. But x times dx miraculously is happening in this du part. It's not a miracle. That is actually by design when trying to anticipate what to cordon off as your u. You want to see whether its derivative shows up multiplicatively in the expression is somewhere else. And indeed it does. This x dx shows up in the integral, which is great. That's why this substitution is successful. Okay, so like to do this, like I can put the 1/2 on this side. And so this piece, this huge chunk, I do the biggest chunks at a time. This big chunk gets replaced with just 1/2 times du. So this gets translated, replace with 1/2 times stuff. I'll take the 1/2 and I'll put it outside. It's a number, so it can come out. It's multiplying, not adding, multiplying. So So du is way over here because that's where the d symbol sits when we just organize our math correctly. And then we just have 1 over u. There, the whole integral got completely transformed. And now, divine inspiration. Just direct inspection. We remember that the derivative of ln x was 1 over u, and so the antiderivative of 1 over u is ln x. I'm going to say a little asterisk here. So this will be 1/2 ln, and here's the thing. Put absolute value of u when someone asks what's the antiderivative of 1 over u. Here is why we put an absolute value. It's because the absolute value is a little bit of a puzzle. Why the absolute value is here? Simply because this function that we integrated, 1 over u, this thing is defined for both positive and negative numbers. And negative numbers. And so its antiderivative should also be a function that has both positive and negative numbers as viable inputs. And we've figured out that the function that works, that's defined on both positive and negative numbers, is not ln u. Ln u is only half the function that's whose derivative is 1 over u. If you want to put the other half of the function all together as one function, you simply stick an absolute value in the argument, and that function works. It'll be like ln u, but like on both sides. The graph will like replicate itself on the other side, and it'll look like a downwards thing like this. Okay? So ln u does differentiate to 1 over u, but 1 over u's antiderivative should have definition across negative u's as well. And the way we fix that is we introduce these absolute values. That's all I want to say about it. That's why the absolute values are there. Okay, so this gives us 1/2 ln, fix the domain issue, absolute value of u. And so this is 1/2 ln of 1 plus x squared, absolute value. Now, 1 plus x squared is never a negative integer, negative quantity in its lifetime. And so the absolute values are just not operating. So you can go ahead and dissolve them. It's always positive, 1 plus x squared. So there you go. And then plus c if you'd like. So that's how you execute this substitution. In particular, pay attention, whoever asked me how to do these substitution problems, pay attention to how I substituted away the dx part of the expression. You differentiate the substitution name, the substitution cipher. Awesome. Fantastic. Okay, so that's perfect. And then you put them all together, add them all together. That's the, split it up into 3 integrals. First one is divine inspiration. Second one is parts. Third one is substitution. Stick them in a stew. Fantastic. Let's go to the topic that we'll be concerned with for the rest of the week. Okay. So I think that was a successful, you definitely saved the Earth. So here you go, your problem. There you go. This animation. Okay. Getting back to the lecture at hand here. Okay. So can we integrate expressions that have sines and cosines in them? How much of this blue dot has, or do sines and cosines expressions live in the blue dot? So let's start with our basic, our starting simple observations. Let's record these in our note card. Okay. First of all, the derivative of sine is cosine. Okay, great. Boring. Resident sleepers in the chat. This is boring. Is negative sine. Okay? So, on the other side, we know therefore that the antiderivative of cosine x is sine x plus c. Let me put a big note card plus c. Okay? That plus c is just all the, I just put it on the note card. Okay, good. So just save space here. Integral of sine x is therefore negative cosine x. Okay, those are just divine inspiration. We're developing our inspiration. Hey, Dr. Young's lab. Math is always boring. No, okay, yeah, good. Dr. Young's lab is a brilliant physical chemist and explains everything really, really well. So go check them out. All right, but okay, insert good comments here. Okay, next. There are more. I think if you remember, the derivative of tangent x was secant squared. Why? Quotient rule. For sine x over cosine x. That's why. Do the quotient rule for sine x over cosine x, and you don't have to believe me, the derivative of tangent x ends up being secant x squared. Now secant x, I remind you, is 1 divided by cosine x. That's all we mean by that thing. Okay, we just gave it a name. Does it sound cool? All right, so it's that. That's what it is, the derivative of tangent. There's another one. The derivative, for example, of secant x. This gets confusing, but the derivative of secant x is secant x times tangent x. Okay, fine, great. All right, so that's great to know. And so, for example, whenever you see the integral of secant squared x, you don't panic because that's tan x plus c, which I did the biggest plus c ever earlier. All right, and similarly, whenever you see this thing, don't worry. This is no problem. Equals secant x. No problem. All right, good. So whenever you just sit down and start differentiating things, you can then gain your divine inspiration recognition software by seeing what the integral says on the other side. Fantastic. Okay, so that's great. So now I'm gonna put an integral in front of you, and it's gonna be a complete nightmare of an integral. Okay, so let's go take a look at a trig integral, and it's just completely a disaster. Here it is, right here. This first one. Wow, what a monster disaster of an integration problem. Cosine raised to the 101 power? That thing's integral? That sounds like a complete garbage can of a math problem. All right, let me get out of the Discord here. So what I'm going to show you is magic. I'm going to show you, do numbers even go that high? That's right. I didn't know 101 was even a legitimate number. It is. So here we go. We're going to sort of tackle this bravely. So let's just see. Here's an example of, can we do this or that integral involving trig functions? We're basically just going to multiply them around and see. Can you do this one? Can you do this one? We'll find that we can do all of them. Okay, so this one. This looks completely impenetrable. Like, what am I going to do? Maybe, okay, here's a tactic you might think. Maybe if I do parts 100 times or something, that sounds like a complete disaster. Like, because there's a product here. There is a product. If I do parts like 10 trillion times, I might get somewhere. Okay, so I'll show you the secret that unlocks this puzzle. And this secret will work for many other puzzles, so pay attention. The secret lies in use what are they called? Trig Identities. This is a general principle for tackling trig for tackling trig integrals, it's a general principle. Exploit the trigonometric identities, all of them that you know. Okay, so that's a general principle, which means to digest that, write that in your note cards now. Okay, here we go. Oh, you don't remember your trig identities? You don't remember them, huh? Don't remember? Chat, does that mean you want to go check them out at the, I mean, I am like a perfect mind. So like, do you want to come check out Sokotoa Island with me? Chat, do you want to go to Sokotoa Island? Students. Yeah? Let's put some music on. Yeah? Sokotoa Island? Let's go? Only one person wants to go. Okay, great. What a boring class. Okay, here we go. We gotta place the neuroimaging software here like this. Hardware, actually. And we're gonna go into the Sokotoa Island here once I learn how to click things on my computer screen here. Just a second. All right. People should be able to see what's happening. Yeah? We're all here? Exclamation point attend. Exclamation point attend in the chat. Spell it right. And you should be in here. There you go. We've got Kotster. We've got B-Boy. Space Cowboy. My little brother is here, who created this whole place. This genius created all of this. Amazing. We've got Rack. We've got Sparky. We've got Grin. We've got Shrek. We've got Smash Time Fools. This is a hardcore mathematician. Very intimidating. Have to behave. They're a moderator. Okay, this person. Yep, lots of people falling asleep. Lots of sleeping people. Math Mama, hello. All right, this is my screen that will constantly be with us. But let's go. Let's go to Sokotoa Island. Don't worry, you're here too. You're here too. Everywhere I go, you come with me. Second row. We made it to the second row. This is historic. Here's Sokotoa Island, folks. It's protected by this force field. Protective force field. These are some succulent plants, I guess. I mean, they're succulent. They must be succulents. And let's look at some basic stuff here. You see here that sine and cosine and tangent are related like this. Here we go. Here we go. We've got our trig identities right here. Nice, perfectly situated for our convenience. All right. By the way, Sokotoa Island also has something called the Wall of Shame. All right. Here's a sample entry in the Wall of Shame. I hope that my students don't deposit other entries in this Wall of Shame. I really hope that my students don't contribute more to this thing. But, you know, we'll never know. All right. Okay, so here we go. Let's see. What I'm going to use is this first famous identity. It's called Pythagoras' Theorem. That's what I'll call it. This one. We're going to exploit this hard in my problem, okay? So this one, sine squared plus cosine squared equals 1. We'll call it Pythagoras' Theorem. Okay, so here we go. Let's go to our teaching screen. And let me now, how do I do it? Okay, I've now straightened it out. Sorry, my hardware fell off my head. Okay, there we go. Okay, here we go. So now I'm gonna, let's deal with this puzzle. The puzzle vanishes magically when we use Pythagoras' theorem. Okay, so the identity that I'll focus on is this one. You'll use this billions of times. All right, good. Because what this says is cosine squared is actually 1 minus sine squared. Okay? And now you might say, well, so what? We don't have cosine squared. We have cosine to the 101 power. Disgusting. What a disgusting puzzle. Okay, no, but look carefully. If you look carefully, you can split this up into 100 of them and then one dangling one. Look carefully what I did. I leave one dangling. And this is conveniently an even power. Because cosine to the 100 is cosine squared raised to the 50. So crumble that. Brilliant. And now use the identity to swap from cosines to sines. This is just magical. It's fantastic. I like this. This is great because at this point, we should be really, really happy. Because this is a U-substitution. Notice how this dangling cosine, this was key. It was key that there was one remaining, because the substitution I'll use is U equals sine x. That's what I'll use. This is awesome. This is amazing. Shouldn't that be 49? No, because cosines 2 to the 50. Absolutely not. Okay. So let me execute that substitution. U is sine x. This is practice for those who asked, how does substitution work? Then you get this part as the dx and du translating bit. Why not 1 minus sine x? Because math mama. 1 minus sine x, 1 minus sine squared x is not equal to 1 minus sine x all squared. These are not equal. Math mama. Do you see what I'm saying? That's why, that's why. That deserves a wall of shame. So I'm going to put that on the wall of shame. Awesome. Well, good. That's exactly what the wall of shame is for. Fantastic. So that's why I chose sine x. Wonderful. All right. So now translate. Translate. So look, we've got here, I'm just taking out all the chunks. Awesome. So this thing becomes integral of 1 minus u squared to the 50. And then whatever. What do I do? 1 minus u squared du. Okay, yeah, white tree. Good. People asking now. Why did I teach U-sub instead of change of base with a Jacobian? Great. Okay. They look similar? Oh, tapioca. This... Yes. Tapioca, yeah. This mistake is adjacent to the other mistake. Yeah, they're all very adjacent mistakes. You're right, tapioca. Tapioca, that's your name now. Now, Y tree, is that the power rule now? Yes. So yes, this is a power rule. So from here, so the point here is now this is this can be dissolved. A bunch of power rules. Meaning, you just like, if you know how to foil this, you can foil it. Hot tamale? Yes, they ask, can you do a further substitution? I probably wouldn't call it what happening to the dangling cosine was absorbed by du. Grin. Du. This ate up the dangling cosine. Yeah, okay. There you go. So can you do another substitution? Okay, and the answer is yes, but with some care. But for now, I just want to leave the problem here because this here is in the zone of simple integrals. Either expand it out, foil it out, and you're just doing power rule 50 times. Or if you're clever, you can do another substitution. The point I just want to make is you can finish this problem if asked. You can just finish the problem and substitute u equals sine x back into the thing. The question we're asking is, can we do a given integral? And this is the pathway to doing it. It's a clever manipulation of Pythagoras' identity. Plus, noticing that this cosine x dx dangling puts us in position to do substitution, a substitution. Also, it was very good that this was an even number of 100s of exponents left over. Okay. All right, good. Okay, so someone asked how I would do it. Okay. I would do it a weird way. So, actually, no. Okay, what I'll do is I'll do that substitution afterwards because it'll take a little bit longer. That's what I'm gonna do. I'll do that substitution afterwards. Okay, so let's keep going. There are two ways to do that substitution, but I'll do it afterwards. Okay, good. So next, we're gonna just up the complexity. Next example. Another example. And what I'm trying to do is get the problem to a simpler place. That's what I'm focusing on. Can we get our problem to a simpler place? It's an example in the similar okay. Another problem. Wow, disgusting. But wait, I'm going to do exactly the same thing I did in the last problem. I'm going to use trig identities and have a dangling piece, and hopefully I can find my way through that way. Okay, so let's do this. So, same technique. All right. Perfect, Evergreen Gamer. Perfect. So let's do this. Okay. So what I do is sine cubed x is odd. An odd power of the sine or cosine. That's the key to all of these, all of the ones that dissolve with this technique. So we use the Pythagorean theorem to replace sine squareds with cosine 1 minus cosine squared, or cosine squared with 1 minus sine squared. That's the utility. And now this part becomes 1 sine x times sine squared x times whatever, cosine to the 4th x dx. And what I'll try to do, the idea is to make this a dangler. Okay, that's the idea. Make this a dangler. All right. All right. Let me see if people are still awake in the class. Are you guys awake? Exclamation point fire in the class. Fire. If you're awake. Yeah. So none of you are awake. Absolutely great. Okay. Fantastic. Good. So no one's fires are going off. Okay, awesome. Let's just keep going then. Okay. Fantastic technology. Okay. What's going on here? So let's make this the dangler, meaning let's put all of this in terms of cosine. Because if we're trying to make sine x the dangling piece that will help when we're trying to do a substitution, we should make everything else in this integral in terms of cosine, and that's what the Pythagorean identity allows us to like transfer between. So for example, this here, I can highlight this red sine squared x, which is magenta or something. That thing we can write as 1 minus cosine squared x times cosine to the 4th x. So this part comes here. All right, and we have this dangling sine x. We're integrating. Fantastic. And now what I'll do is, of course, I'll do a U-substitution, and it only works out because of the dangler. It's so convenient. It works out so beautifully because of the dangler. Yeah, that's right, Y-tree. U sub cosine x. Now, the derivative of cosine x is negative sine x. But that's good enough because here is that little piece. Okay, so negative du, for those who have trouble with substitution, I'm doing it painfully slowly now. So negative du is sine x dx. Here we go. So I'll inherit a negative sign. Du is taking care of that stuff, the dangler. And now I have 1 minus u squared times u to the 4th. Okay, that's interesting. That's fun. This time, the algebra is simpler than the previous problem. There isn't that much foiling to do, or distributive law. So I'll just go ahead and do it live. And now it's just anti-power rule. Translate back. Boom. Done. Okay, what did we just do? We just noticed that this crazy integral, this one, the product of this many powers of sine and that many powers of cosine, this integral is in the pale blue dot. We do not have to panic when we see this integral. It's in this sense that we're knocking down trig integrals. Look, I took sines and cosines and I multiplied them in some weird way, and I was able to execute. Okay? Amazing. Yeah, Udo takes that. It is amazing. It's so satisfying to see this. Okay, so with that, let's depart the Sokotoa Island. We will be here many times this week. We'll probably need to add a couple more identities, the double angle and half angle identities. And we'll add another entry here to the wall of shame. So that's great. Okay. Thank you all for participating. Oh, this is interesting. Okay, good. So let's zoom out of Sokotoa Island, our amazing little oasis, our oasis of safety. Wow, this thing even has roots. Check this out. There's even roots here underneath. That's remarkable. That's some detail right there. There are roots in Sokotoa Island. That is really cool. It's really accurate. All right, let's get out of here, class. Let's get out of here. Okay, we're back in the middle of the worlds, I guess, or somewhere. Okay, and now I have to end the program and come back to teaching. Okay, so that's 12:15, 45-minute lectures, fantastic. We've gotten to the point where we can do sine cubed of x times cosine to the fourth. We can do cosine to the 101 power in principle. Odd powers of cosine or sine are our friends. So that's the summary. The summary. If you want a jingle, odd powers of cosine or sine in the integral are our friends. Okay, so the next problem that I'll start off in the next lecture with is, so we should probably look at something like sine squared, for example, or cosine squared. How to crack these. Or sine to the fourth, or sine squared times cosine to the fourth. These puzzles will be where we start off on Wednesday in this week of which trig integrals can we unknot. They gave us a little puzzle, like a knot. Which of these integrals can we actually manipulate and problem solve our way through with the help of trig identities and substitutions? That's substitution and maybe integration by parts. Who knows? We'll see. Okay. All right. So let's see. Now I'll switch to chat. Chat is over here. Okay, let me now look at chat and see what kind of degeneracy happened. What an interesting classroom. Yes, it is. It's my third eye. It is the perfect vision that's present here that my students think I practiced. I didn't do any practice to get. So I'm just giving them that immediately and finally capitulating to them. That's that. Oh, Gath is here. Shout out to Gath. Gath is a excellent organic chemistry streamer. She's got it going. Many of the ideas that I have on stream are just stolen from Gath, so that's great. Yep, I think I've answered. Everyone in class is sleeping? That's right, everyone's resident sleeping. So Hot Tamale wants to add to the wall of shame. Yeah, everyone should try to add to the wall of shame. The wall of shame is secretly the wall of strength. I have made all varieties of shameful mistakes. I mean, I was like 3 years old, but yeah, I have. And I remember them. Okay. Awesome. So this chat looks like it's done. Let's check our redeemings. Good. No one has redeemed anything. That's fantastic. Can we do that homework now on WebAssign? Oh, yeah. I mean, it should be. Wait, is the Trig homework available? It should be. Oh my god, man! I have never had trouble with WebAssign. This whole time, and for some reason, and I have a suspicion why it's happening, but I don't want to say it. But when I ported over the two assignments, complete disaster happened. But okay, class, tell me, do you see Trig integrals as scheduled and available for this week? It should be available. Yeah, forget 1 and 2. 1 and 2 had a crazy story that I have my suspicions, but 1 and 2 was just a shit show. But 3, let's try to make 3 and beyond be correct and fine and not duplicated. Does everyone see number 3 visible, due Saturday? You can click it and view it and everything is working. Awesome. Good. So let's keep that in our minds. And if it suddenly duplicates, we know that it's some people in the department who are poking around in my WebAssign. Some people that I have to be nice to and respect and all that. But I suspect that something terrible happened around Friday evening, Saturday morning from one of those people that I respect. Thank you, boss. But don't click anything in my WebAssign. Okay. Respect. Good. Fantastic. Okay. Homework 3, totally fine. No issues. There's only one of them. Everyone can see it. Let's keep it that way. All right. Fantastic. Okay, so what we have here is a question from someone named Stacksmaster. Okay, so Stacksmaster. Grin, go ahead and just do 1. I will look. It'll show up in my WebAssign gradebook. It will show up. It may not show up in yours for whatever reason, but it is showing up in mine. So do 1 of them. And then at the end, I will just take the one you did and then make it the score and remove the other one that's just empty. So it will not affect you if you only do 1 of them. But you gotta do it. You gotta do it, at least 1 of them. Good. It will show up. Either are showing up on my end, so it's good. Okay. It's a complete shit show what happened with the WebAssign. But it's not gonna happen again, because we're actually just gonna not duplicate. Boss. Whoever duplicated, we're not going to do that again. Right. Good. Okay, so Stacksmaster asks a good question. Hi, BMP. I, a very smart internet user who is very smart, was wondering your opinion on Lord Grumpelgwark's 18th theorem on biramoral calisthenics and their cosmic linearity relating to alembic causation of independent tensorform and seriforms. I intend to impress you and intimidate your students and thus make myself feel better about myself. So this comment is from a former student of mine, Stacksmaster. Stacksmaster's life goal was to become VIP. So thanks to that comment, they have impressed me so much that I've decided to grant them VIP. So there you go. Here's your VIP. I'm Stacksmaster. Yeah, same with the prerequisite. It's not a test. It's like it's just an assignment. Yeah, it's just an assignment. Hype Ghost. Okay, yeah. Smash Time's emote game is incredible, I have to say. Three is Pog? Wait, what question am I dodging, B-boy? What question? What am I dodging? Tell me. Don't just drop that. Yeah, what am I dodging? Yeah, the prerequisite is another homework, and just do one of them. Okay. Oh, they're hype train emotes. Damn. That's awesome. That's incredible. I have not witnessed many hype trains out in the Twitchverse. Wow. Okay, followers. Oh, bike till the heart explodes. I will do that. Thank you, Smog. Thank you, Classic Nations. Thank you, Rock Deck. Thank you, Imigrosic. Thank you, Bao Secreto. Thank you, Wenithor. Thank you, Cambrox. Thank you, all these people, for following. That's great. And Battling Storm 4 has somehow accumulated enough points to bike till the heart explodes. I'm going to do that. That's how stream is going to come to a close, unless people request other things with their channel points. But I never stop teaching, so I'm going to go here. Bike till my heart explodes. Everyone, get up and do some exercise. This era of COVID. 6 feet away from everyone, though. Don't exercise near people. Seriously, don't do it. Okay, here we go. Today, what did we do? And what did we did? Well, we learned how to integrate exactly 2 puzzles. The puzzles involved sine and cosine. Different powers of them. What was key to unlocking these puzzles was that one of the sine or cosines had an odd power, because then you can cut out one of them to be the dangling bit. Then the rest of it, you can use the power of the Pythagorean identity, which is located in Sokotoa Island. You can use the power of that identity to replace the rest of the integrand in terms of the other trig function. And then substitution gets you through. It's brilliant. It's an awesome strategy. But what the heck do we do about the other integrals? Like sine squared, or cosine to the 4th times sine to the 8th. Oh my god. No odd powers. What are we gonna do? Well, stay tuned on Wednesday, where I show you how to deal with that. Okay. All right. Wow. That was a real workout. Okay, let's get out of here. let's get out of here, folks. That class is over a long time ago. And okay. Can we get the dictionary out? Yeah. Okay, good. Power within. Absolutely. Everybody wants to be VIP. Great. All right. Now, folks, I have to discard you, folks. I have to drop you all off somewhere. Let's go see what's out there on the Twitch education universe. Let's see who's out there. Professor Melko. Professor Melko is live. Awesome. One of the OG ancient Twitch streamers. One of the first people. Oh, thank you for the follow, Marilyn Fennel. Thank you. One of the OG original streamers. His stream inspired me to try. Inspired us. My little brother is key in this stream to try to make our stream fancy looking too, and filled with little fun things. Professor Melko. Go say hi to Professor Melko and share your respect, the great respect you have for me. Go and reflect it over at Professor Melko's stream. Learn some physical chemistry. Let's go do that now. Starting the raid. Get going. Get going over there. Everyone, go say hi to Professor Melko. One of the OG educational streamers. Okay, so now it's going to cut off randomly like it usually does.